Welcome to the Explainer. Okay, I want you to literally forget everything you think you know about your morning routine. Just toss it out. We're going to shatter your worldview just a bit here. Because when you wake up and stumble into the kitchen, you are not making a morning beverage. You're definitely not practicing some culinary art. You are, in fact, executing a highly specific scientific protocol. So, today, we're going to learn how to properly engineer the absolute perfect cup of coffee.
Okay, let's dive right into this. To completely change our paradigm, we really need to wrap our heads around one absolutely crucial concept. Brewing coffee is a straightforward chemical solvent extraction. That's it. Hot water is simply your solvent. And your one and only goal is to use that solvent to literally wash soluble flavor compounds out of roasted cellular cellulose, which, is really just a fancy, scientifically accurate way to describe a coffee bean. If you treat this like cooking, like, a dash of this, a pinch of that, close enough, you're going to fail. We need absolute precision here.
So here is our lab manual for today's explainer. First, chemistry, not culinary art. Then, phase 1, the golden ratio. Phase 2, the grind. Phase 3, thermodynamic execution. And finally, troubleshooting the brew.
All right, let's kick things off with section 1, chemistry, not culinary art, and specifically the stakes of temperature. We really have to throw out that whole artistic approach because chemistry requires exact variables if you want a proper reaction, right? And this brilliantly illustrates why precision matters so much. Just look at these two super common temperature errors. If you use one of those cheap standard drip machines, the water it spits out is generally way too cold, usually hovering around 180 degrees Fahrenheit. As a solvent, it's just too weak at that temperature, and that leaves you with sour, under-extracted coffee. Yuck. But on the totally opposite end of the spectrum, if you just use a kettle of furiously boiling water right at 212 degrees, the solvent becomes way too aggressive. It strips away these heavy, astringent tannins from the cellular cellulose, leaving you with a harshly bitter cup. You absolutely have to hit the exact sweet spot right in the middle.
Moving right along to section 2. This is phase 1, the golden ratio, or, as I like to call it, the universal mass equation.
Now, you might be wondering why we can't just use a scoop. Well, because coffee beans vary wildly in density depending on their roast level, volumetric measurements are completely useless. A scoop of a dark, oily roast weighs significantly less than a scoop of a dense, light roast. So seriously, put away the scoops. You need a precision digital scale, because here is the massive number you need to burn into your memory, 1 to 16. This right here is the scientifically established constant extraction ratio, 1 part coffee to 16 parts water, calculated entirely by weight, no exceptions.
To put that into a practical perspective, let's look at the exact payload required to brew a standard 1-liter pot. Following our 1 to 16 golden ratio, you're going to need exactly 60 grams of freshly roasted whole bean coffee and exactly 1,000 grams, which, super conveniently, equals exactly 1 liter of water.
Now, let's talk about the solvent chemistry itself. You might be sitting there thinking, hey, I'll just use the purest water possible, like distilled or reverse osmosis water. Do not do that. Seriously, don't. Pure H2O is actually way too aggressive of a solvent. It completely lacks the magnesium and calcium ions that are absolutely mandatory to chemically bind to the coffee's flavor compounds. So what do you need? You need filtered tap water or spring water with a total dissolved solids, or TDS, count of roughly 150 parts per million.
All right, on to section 3. This is phase 2, the grind, which is all about surface area calibration. Because our hot water solvent needs access to the cellular structure of the bean, the literal size of your coffee particles dictates exactly how fast the extraction happens. So, here's a massive warning. Never, under any circumstances, use a blade grinder. They don't actually grind. They just violently shatter the beans into this chaotic, horrible mix of microscopic dust and massive boulders. What you actually need is a conical or flat burr grinder. A burr grinder precisely calibrates the beans to a beautiful, uniform, medium consistency. If you touch it, it should feel exactly like coarse sea salt or rough sand.
So the crucial point here is understanding the exact consequences of poor surface area calibration. If you went ahead and used that blade grinder, well, that microscopic dust is going to instantly over-extract the second the hot water hits it, turning your brew horribly bitter. Meanwhile, those massive boulders, they're going to stubbornly under-extract, which adds these awful sour notes. So you end up with a cup that is somehow, miraculously, simultaneously bitter and sour. It's the worst of both worlds. Consistency is literally everything here.
Okay, moving to the climax of the explainer. Section 4, Phase 3, Thermodynamic Execution, also known simply as the brew.
For absolute control, and we're assuming here that you're using a manual pour-over carafe like a Chemex or V60, or maybe an SCA-certified precision batch brewer, 205 degrees Fahrenheit is your absolute non-negotiable target temperature for that 1,000 grams of water. That's 96 degrees Celsius for my metric folks. Now, if you don't have a fancy kettle that lets you dial in the exact temperature, don't worry, there's a super simple scientific workaround. Just bring your water to a rolling boil, take it completely off the heat, and let it sit for exactly 60 seconds. Boom, you'll be right in the perfect target zone.
Now, the actual thermodynamic procedure is mapped out in 3 very precise steps. Step 1 is the thermal flush. Step 2 is the degassing bloom, and Step 3 is the controlled drawdown. Keep in mind that from the very first drop of water to the final drip, this entire process should take exactly 4 to 5 minutes. Not 3, not 6, 4 to 5. Let's break these steps down.
Step 1. The thermal flush. Before you add even a single grain of coffee, you need to pour some of your hot water right through the empty paper filter. This actually serves 2 absolutely vital purposes. First, it washes away that papery, woody taste of the dry filter so it doesn't taint your extraction. And second, it preheats the glass carafe, which prevents the thermal shock that would otherwise rapidly cool down your final brew. Oh, and always remember to discard this flush water before moving on. Nobody wants paper water coffee. Next up is the degassing bloom. See, coffee beans trap massive amounts of carbon dioxide during the roasting process. When hot water hits them, that CO2 violently escapes. If you just dump all your water in at once, that escaping gas is going to actively push the water away, completely preventing any extraction. So we bloom. You pour exactly 120 grams of water, which by the way is double the 60-gram weight of your coffee, straight over the dry grounds. Gently swirl the resulting slurry to wet any dry pockets. Then just stop. Wait exactly 45 seconds. It's actually super cool to watch. The bed of coffee will literally swell up and bubble as the gas escapes. And finally, we have step 3, the controlled drawdown. After that 45-second bloom finishes, you are going to slowly pour your remaining 880 grams of hot water. But you want to do this in gentle concentric circles. The whole goal here is to maintain a nice steady water level in the filter. That ensures a consistent thermal mass, which guarantees a perfectly even, steady extraction all the way through the bed of coffee.
All right, let's wrap this up with Section 5, Troubleshooting the Brew, or what I call the Red Team Report.
Let's move to our troubleshooting table and see how this all builds together to fix the 2 most common catastrophic errors. Let's say you've executed everything perfectly, but your dark roast still tastes bitter. Well, my friend, you've encountered the French roast variable. Dark roasts have a highly porous cellular structure because they've been physically compromised by the roaster's extreme heat. That means they extract way faster than light roasts. So the correction? You must drop your water temperature down to 195 degrees Fahrenheit and coarsen your grind just slightly to slow down the extraction of those harsh tannins.
The second issue is what I call the hot plate catastrophe, and honestly, it is absolutely devastating to the chemistry of your brew. If your coffee tastes absolutely perfect at minute 5, but tastes literally like battery acid at minute 45, the hot plate is 100% to blame. Most standard drip machines use a glass warming plate, right? Well, that plate constantly applies direct thermal energy to the brewed coffee. It is literally cooking the delicate chlorogenic acids present in the liquid, forcefully breaking them down into crofaic and quinic acid. And those 2 acids are highly sour and deeply bitter. So golden rule, never ever leave your brewed coffee on a heating element. The very moment it finishes extracting, you must immediately transfer the brew into an insulated, vacuum-sealed thermal carafe to preserve the chemistry.
So, having seen the actual science, and having looked at the exact universal mass equations and thermodynamic steps required, are you ready to ditch your hot plate drip machine for good and finally execute a proper chemical extraction? Tomorrow morning, remember, you aren't just making a drink, you are a chemist running a protocol. Thanks for joining me on this explainer, and good luck in the lab.